Okay. Good afternoon, everyone. I hope you're doing great. This is the last lab. What I'm going to do, we quickly review in 5 minutes and then bring to the part that we needed to start working on. After that, we are going to spend time with people that are in the class to see if they have any concern on their projects and so on. Before anything else, because this is the last lab, you might ask that, okay, how about the lab next week? The lab on next week will be dedicated to going through the marks if anybody has any concern, any question, any problem. So the next week will be dedicated to that. And the lab would be online. So I will share, if I can, one link from 8 in the morning all the way to 6 in the afternoon, while between 11 to 1, I'm gonna take a rest for lunch, but the rest would be like that. And hopefully in that day, you're gonna receive an Excel file plus a video that you can simply go through your marks the way that you want to see how the formula works. And that's pretty much it. So if there is no any question, there is no question, or we can just continue. Let me just close my camera. There we go. Okay. This is the first real project that we started working on, cat and dog, with real data set that it's not part of Keras and we need to import. We went through the first way of using convolutional neural nets after copying cats and dogs into training, test, and validation folders into two different classes, cats and dogs, and checking. Then we created the first convolutional neural nets. As you see that here, we have max pooling, conv to the max pooling, conv to the max pooling, and so on. After that, we flatten and we just use these two layers. The first one is the hidden layer, and that is the output that has one neuron because we have cats and dogs, and the activation should be sigmoid because it's just binary. And this is the summary of the network, and this is the RAMS prop and learning rate, and the loss, well, binary cross entropy. And after that, when we ran the project, we saw that we got to something like 70% with just simple technique. And then after that, we started using the augmentation, and overfitting is caused generally by having just a few number of samples. That is why the augmentation idea is to reuse. Imagine that we have one cat picture. We are gonna crop it, tilt it, zoom in, zoom out, do all these things. And in every epoch, we are going to use not the original picture, but a remix of that. So that's a good thing. That is why if you see, for instance, a cat towards up or tilted, or you can just recognize all those patterns as well, right? But because you remix the original picture, how could you eliminate the conspiracy that could happen among the cells? That is the dropout. And after that, you see there is a big jump here. So we see we have kind of close to, well, we have 80% which is crazy. That's a great improvement from 71 to 84.5. Like, as it mentioned, 14 neat, clean improvement. But still, and even if you just do any manipulation like regularization and so on, it's not going to get anything more than 86, 87. So we said that, how about reusing another data sets and other models that we have used before? So imagine that somebody created a network over ImageNet, and ImageNet contains 1.4 million pictures, which they are in 1,000 different classes. One of the versions, one of the models created by Simonian and Zisserman is called VGG16. And we are going to reuse that. But for reusing that, we have two major approaches. One is feature extraction, and the other one is fine tuning. So we talked about the feature extraction, and we said one of the normal ways of feature extraction, if I show you, it's like we are going to get the pictures, like 2,000 pictures, we bring them into convolutional base, and we are going to have 2,000, Nicholas, we are going to have 2,000 strings, like flattened 8,192 units, right? So technically we use, how many times we use this convolution? Just one. We bring 2,000 pictures in that tunnel once, and we are going to have 2,000 a string, that each string has 8,192. And if you say that, Reza, where did you get that that 8,192? Look at the last layer that we have here in that convolutional base. You see that? So let me just show you. If I say 4 times 4, which is 16, times 5, 12, it's going to give us 8,192, which has come from this, right? This is one approach. But let me ask you one thing. How could we create augmented pictures? Nicholas and Rachel, if you want to step in and talk about this one, please feel free to open your mic and talk. Also, Malik, my online fan. Okay, yes. When that happens, that's correct. But when that happens in these steps, convolution happens in here between this place all the way that we get to this place, right? From if I can okay, now I have a good picture to show. Look at this. The augmentation happens, for instance, in this picture one, we augment it, we change the shape, and we bring it and make one of those 8,900 some pixels. Augmented version of it is going to convert to this one. Then this is the first round. If the epoch is from here all the way to the end. Second round, we are going to use the same picture and we are going to augment it. We use another, tilted this time, zoom in this time, whatever, right? We bring the second version of it, third, fourth, fifth. But when we just go through this one time, is there any place that we can augment? No. We just get the original picture, bring them into the convnet, and make that one 8,000 something. So this very expensive part happens once. We have no remix of the original picture. That is why, but the good thing is this part is what we borrowed from where? From VGG, right? It is already learned from somewhere. It is already learned from somewhere. That is why we don't start from random numbers. Look at the result. I have already explained the algorithm here, but the result shows quite fascinating result that from 80 something, we get to almost 90%. You see that? It's almost 90%. But what is the gap? Why we have this big gap? Anyone at home or Nicholas here, can you explain why we have this gap? We actually have overfitting almost from the start of the journey. The reason is we do not have any augmentation. We didn't do any dropout. Augmentation is one of the tools that we could use to lower down the gap, right? We don't have any augmentation. We don't have any dropout. So that's the result. Yeah, let me just show you the epoch. Let me just go a little bit higher. Yep, just imagine what we borrowed is VGG, and for the weights we used ImageNet. Means that, hey, use the architecture of of VGG using the ImageNet, that 1 million point 4, 1.4 million. Anyway, by saying that, by using that mechanism, we got to this great number, but it says that the plot also indicates that you are overfitting almost from the start, despite using dropout with a fairly large rate. That's because this technique doesn't use augmentation. And after that, it says that extending the conv base model and running it end to end on the input means that, how about this model? We get all the pictures and then go through end to end. We are going to go from here all the way to here. Does that make sense? Yeah, we go from here all the way to here. In that case, Nicholas, can we have augmentation, yes or no? It is going to be end to end. So are we going to have? Definitely yes, because the epoch will be from here to here, not in the previous attempt, it was from here to here. Because we have all the convolution plus densely connected layers all in one epoch, here we can have augmentation, means that first time you use the picture, second time you use a remix of the picture, another remix of the picture, another remix of the picture. In each epoch, you're not going to use the same picture 2 times. Does that make sense? Rachel, Malik, is it fine? Everybody? Let's just have the chat. Okay. Awesome. Great. So in that case, what we do actually, we place that convolutional base. Remember, this conv base, if you look, has come from this page, which is page 145. Let me just mention. Okay, so this is that VGG. And if you go to page 145, you see that it provides 14 million parameters. So that is why if you say, show me the summary of the model, it says 14 million parameters. Does that make sense? But there is one fact. If you use any model, by default, you can change the weights and biases. That's by nature. We have convolutional neural nets and densely connected layers to be able to change them. But what if you don't want to change them? Now think about it, why we don't want to change the weights and biases of conv 2D and max poolings of the convolutional base. Let me just have your beautiful names here to make sure if you want to step in and talk about this. I repeat my question, why we do not want to change the weights and biases of convolutional neural nets? Okay, let me tell you, because this model is already trained by 1.4 million pictures. We want to reuse it. We don't want to destroy it, right? We want to reuse those weights. Listen to this. It says, before you compile and train model, it is very important to freeze the convolutional base. Freezing a layer or set of layers means preventing their weights from being updated during training. If you do not do this, what's going to happen? Effectively, you're destroying the representations previously learned. Why that is happening? Why it destroys the previous one? Because at the beginning, the weights and biases are random in dense layers, and they are very far from what we expect. They are false, right? At the beginning, random numbers. Because the dense layers on top are randomly initialized, very large weight updates would propagate through the network. Because they are very off, you need to use Ram's prop to correct them, right? And because the first steps are huge, they're going to propagate from where you are all the way to the input, including the convolutional base. Unless that you say, hey, no, freeze, don't touch them. Does that make sense? We don't want them to be impacted. So if you say conv base dot trainable equal false, before saying that, the number of trainable would be 30 layers. But after saying that, the number of trainable would be 40 for this structure. Let me show you one thing. What page are we in? 150. So let me see if I already have that. Okay. Okay, here is the place. We say, show me the model.trainable weights. It shows that we have 30 layers. But if you say conv base trainable, conv base was which part? Nicholas, conv base was this part, right? If we say, hey, freeze that part, how many other layers we have? Just two. If you say conv base trainable equal to false, means out of 30, except for the rest should be frozen. How many left? 4. But why 4? Look, how many layers do we have in this toy example? We have just 2 layers in the example that we have. 2 hidden layers, right? We have just 2 hidden layers. So one weight for this, one weight for this, one bias for this, one bias for this. Does that make sense? Totally 4 layers. And it is mentioned that 2 for weights and 2 for biases. With this setup, only the weights from the 2 dense layers that you added will be trained. That is a total of 4 weight tensors, 2 per layer. The main weight matrix and the bias vector. Okay. Let's go to this part. Fine tuning. Nicholas and people at home, please read this paragraph and see what you can understand from it. And I want your opinion to be shared. What does it say? It says that fine tuning consists of unfreezing a few of the top layers of a frozen model based used for feature extraction and jointly training both the new added parts of the model. First, before understanding, so the added part of the model and those top layers. This is the shape of the convolution that we are using. Let me just type somewhere. If I say VGG 16 architecture, this is the thing that we have. We have 16 white and green layers. Am I right? We have 16, now it is gray and okay. Look at this example. This is the filters in the first layer, in the first 2 conv 2Ds. Are they specific or are they general? Nicholas, what is your opinion? Can you see any face here, for example? Can you see any specific thing, or they are general line detectors, edge detectors, and so on? They are general. How about this? It's layer 2. It's still general, but a little bit more complex, right? But what if I go higher? Now it is going to get more complex, right? And if you get to the layer number 4, then it is, I mean, block number 4, it is quite complex. And in the next block, it is going to get very much close to, for instance, ears of human, nose of human. You cannot use that very much in something very far like cat and dog. Does that make sense? So the idea is instead of freezing all these filters, all these layers, let's freeze the first four blocks and just unfreeze the last block. Okay? For doing that, it says that why not fine-tune more layers? Okay, now the question here we said instead of freezing all these layers, let's just freeze the first four layers. And because the last layer of conv2d is very much abstract, let's say we can tune this part, we can manipulate the weights and biases in this one. Okay, it says that if the classifier isn't already trained, then the error signal propagating through the network during training will be too large. And the representation previously learned by the layers being fine-tuned will be destroyed. Thus, the steps for fine-tuning a network are as follows. So what we normally do, this is our layers. Then we are gonna fine-tune the block number 5. So it says that you'll fine-tune the last 3 convolutional layers, which means all layers up to block 4 full should be frozen, and just block 5 conv 1, block 5 conv 2, and block 5 conv 3 should be trained. Why not fine-tune more layers? Why not fine-tune the entire convolutional base? If we fine-tune the entire convolutional base, then what is the use of using a trained convolutional, right? We want to reuse those filters, those feature maps. We don't want to invent everything from the scratch. Earlier layers, it says that earlier layers in convolutional base encoded more generic reusable features, whereas layers higher up encode more specialized features. That is why, that's one of the reasons. The other thing is, the more parameters you are training, the more you are at risk of overfitting. If you say that, hey, you know what? Let's not freeze, let's change all the convolutional layers. Means what? Means you are going to make it specific to data in hand, overfitting. And apart from that, you need to train everything. So it is expensive. That is the other reason that I have added here. So it's going to be an expensive process. Look what they have done for this layer, for this job. They said, let's say convolutional base, that's what we call it in page 145, conv base. Dot trainable equal to true means no freezing. Unfreeze everything. But wait, we are going to say set trainable equal to false. What is set trainable? It's just one parameter. We say for layer in conv base dot layers, we have layers, right? if layer name is equal block5 conv1, then trainable is equal to true, means you can train it. Else, if set trainable is true, means for the rest, then layer dot trainable equal to true. Remember, we say if the layer name is block this, set trainable equal to true. And if trainable, then change the layer dot trainable equal to true. Else, if we are in block 4, for example, the trainable is equal to what? False. In other words, freeze any others. Guys, this is only to explain this. Means first, make everything creamy, trainable. Then say if it is in block 5, 1, and the rest of this block, make it trainable. Else, make it not trainable, freeze it. That's just for that part. There is one fact. Here we use learning rate, a very small number. Why we do so? It says that, hey, the reason for using low learning rate is that you want to limit the magnitude of modification that the RAMS prop or optimizer applies. Because if the steps that you take by optimizer is huge, then whether you want it or not, it's going to drastically change the weights and biases of the previous layers. We don't want huge, crazy changes. We want tiny, small changes in each step. Does that make sense? Okay. It says that exponential moving average of these quantities, it says to make them more readable, you can smooth them by using this approach. You see, here it shows it is very noisy. By applying that fine tuning, we get to something like that is crazy, like 97%, 96, 97%. But it is not very much readable. I want you to spend a few seconds. I explained similar thing there. The factor was just 0.9. Here it is 0.8. I want you to spend a few seconds and see if you can understand the code. Okay, thank you. You have an idea? Look, we have some points that we want to change, right? Imagine that we have 100 epochs. In this example, we have 30 epochs in this example, right? We have 30 epochs here. It doesn't matter how many numbers we have. What we do is we say, okay, for every point in points in accuracy, for example, if we have a point, if a smooth points, then do what? Go to the previous one. This is a very important condition. What does it mean? If smooth point, at the beginning, it is null. At the beginning, it is null. If it is the first step, do we have any smooth points? No. Then get that point and add it to the smooth point. So after the first round, we have something. So we don't go through this anymore. We always get to this part. So it says that, say 1 point before this, -1, call it previous. Call one step before, previous, and give that previous 80%, 80% weight, 80% weight for that previous, and for the current point, give it 20% weight. And do that for the next, do that for the next, do that for the next. What does it mean? It means always you deal with the history. It's not going to be a drastic change. It's going to make it smooth. The more that you increase the factor, the previous point has higher importance. Does that make sense? Right? Okay. So after applying that, look at the line here, look at the line here. After applying the smoothness, you're going to see how smooth it is, how smooth compared to the previous one. And for this one, now you see that it's crazy for the loss. For the loss, here we are dealing with a kind of fluctuation, but it says that, look at this. What you display is an average of point-wise loss values, but for the accuracy, what we deal with is the distribution of loss values. So again, here we deal with distribution of loss. That is why there is no very much noise. How about here? Here we use the average. Look at this. It might look like a huge gap, but guys, look at the percentage. It is 97.5, and this is 99.5, 2%. It's not a huge overfitting. So overfitting is reasonable, not huge. After that, we get to the conclusion of this that we have done so far. It says that convnets are the best types of machine learning models for computer vision tasks. It's possible to train one from scratch, even on a very small data set with decent results. On a small data set, overfitting will be the main issue. You remember cats and dogs, we had a small data set, so 70-some% would be the best that we could get after data augmentation. So data augmentation is a powerful way to fight overfitting when you are working with image data. And after that, it says that it's easy to reuse an existing convnet on a new data set via feature extraction. So we use feature extraction and it brought us to 90% almost. This is a valuable technique for working with a small image data set. As a complement for feature extraction, you can use fine tuning. You remember feature extraction had two approaches. One is end-to-end, expensive one. One was going through the convolution once, but epochs happen on the densely connected layers. Anyway, but the best is as a complement to feature extraction, you can use fine tuning, which adapts to a new problem. Some of the representations previously learned by an existing model. This pushes performance a bit further. By saying that, we get to visualizing what ConvNet learns. For this part, I do not want to deal you with a algorithms and code. I just want to say we have three forms of visualizing. Visualizing intermediate ConvNet outputs. So we are going to get the output of visualizing after applying each filter, visualizing the ConvNet filters, and visualizing the heat map that shows where the object that we could detect locates. So the output of the layer is often called the activation. Let me just quickly tell you, going through all those cats and dogs pictures, we pick one. And then for the first time, we say that go to a layer in model.layers that we created a few seconds ago. And for the first time, the output of this, we have one input, but the output is 8 different layers. For getting there, you can just upload this file, 160 to 166. So I strongly recommend, you already have it in the Telegram as well. Please go to Colab. Control O, upload, and get this one. Okay, take your time. Download that. Done. In the Telegram, we have Telegram. Okay. Where I have sent in a package as well. Zip, but it takes a long time. Not a bad idea. You can just simply go to one browser, and type web.telegram.org. Enter, and it needs your phone. And then you can simply download it from there. That's the shortcut. Okay, Rachel, can you? Okay, I'm gonna send it to you here. And we have it on Telegram as well. So you can download it from the chat as well. If that is not possible to use Telegram, you can use there. Okay, Rachel, whenever you finish, please give me a signal. Okay, awesome. Bring it to, did you bring it to? Okay, lovely. Let's run it together Okay. So after running that and getting to this, we are going to see that's a cat image, right? Now, in the next part, that is the part we say that for every layer in model.layers. And what is that model that you're talking about? Please look at here. We said load model from that cat and dog small keras and place it into model. Do you remember the model that we created, cat and dog, and we saved it? Here, it shows that conv2d max pooling, conv2d max pooling. That's the first model that we saved. And in this part, we say, hey, for every layer in model.layers from 0 to 7, not 8, take out those models. It's going to be the result. From 148, 148, then 74. This is max pooling. Again, conv2d, max pooling, conv2d, max pooling, conv2d, and max pooling. So these are all the outputs. And look at this part. We say, guys, I set first layer activation. Let's call it activations 0. Do you see that? We have activations that contains, it says activation model. What is this one? Activation model. Look at this. We have layer outputs, and here in activation model, we say for inputs that we have, consider layer output. So every picture should go to 8 different layers. You might say, I got confused. Don't worry. We have 8 different activations, layers of activations. Layer 0, let's call it first layer activation, means, Rachel, means going to this layer. This is the first layer. Does that make sense? This one. Conv2d, conv2d, 148, 148, 32. This is the first layer. How many, tell me, how many channels do we have? 32. Lovely. Awesome, Rachel. Thank you. So look at the next part. How many channels we have in the next part? 32. This is layer 1. This is layer 2, right? So here I said, let's call it, I mentioned it here, first layer activation. Then I said second layer activation. And then do you see that first layer activation shows 148, 148, and then 32. The second one shows 174, 74, 32, and so on. Look, what if I say first layer activation, go to 0, all the pixels, and then I say filter number 4. Let me show you one thing. Rachel, what if I say, instead of 4, 0, is it going to show another filter? Yes or no? Yes, it is going to show another filter. What if I say 20? Is it going to show another filter? Yes, it does. What if I say, Nicholas, what if I say 30? Is it going to show another filter? Yes, it is. How about 31? How about 32? Actually, 32 gives you error. Why? Because 32 channels, 0 to 31. Right? So, yes. How about the next layer? You remember the next layer? And let's just use the same thing like 4. And for this one, let's just use 4 as well. Do you see these two are almost the same, but this one sharpened those edges? Does that make sense? How about this one? This one is going to grab more intensified. The next layer, that's funny. If you say 40, it's going to accept. If you say 60, it's going to accept. If you say 64, is it going to accept? Because it is from 0 to 63. So 64 is not included. Does that make sense? And this is going to be some other examples. And we just wanted to show here how many cats we have in one row? 16. Because we have 32 channels, we are gonna just show all those 32 in 2 rows. The second, you remember it was 32 as well, but the next one was 64. So we are gonna, yes, lovely, Rachel. Excellent. And the next is 64 as well. But look at the next one. It's going to be 128. And then 128 and 128 and 128. Does that make sense? The code is a little bit confusing. It needs a little bit of time to go through it. And there are 2 parts that says multiply 64 plus 128. If you say, let's comment these 2, then the result would be something like that. We cannot easily read them and see them, what is happening. This is just because of these 2 that I wanted to see what is the impact of them. And the last thing, so let me just quickly see if I have covered everything. There's one thing, guys, the number of images in row was 16. The features, for instance, for 32 is 32 divided by 16. So it's going to make it 2 rows. 2 rows. But listen to this. This is number of rows technically, not number of columns. It's going to be 2 rows of 16 pictures. The last, and we saw that the lower layers, they are responsible for more generic things. The more that we go higher, it's going to be more specific, like ears, eyes, and so on. So the lower, more edges, more information. The higher, more abstract. It says that as you go higher, the activations become increasingly abstract and less visually interpretable. So less information about the visual contents, increasingly more information related to the class of the image, like cat and dog. The more that we go higher, it's more abstract. The sparsity of the activations increases with the depths of the layer. In the first layer, all filters are activated by the input images, but in the following layers, more and more filters are blank. The reason for that is You have a filter that your picture cannot get through and anything comes the other side. For instance, your filter shows ears, but you don't have ears in the picture, right? This means that the pattern encoded by the filters isn't found in the input image. And the features extracted by a layer become increasingly abstract with the depths of the layer. A deep neural network effectively acts as an information distillation pipeline with raw data going in and being repeatedly transformed so that irrelevant information is filtered out and useful information is magnified and refined. What it wants to say is all of us have seen a bicycle, but if I ask you, okay, don't look at the bicycle and draw something. First, you are going to draw two circles and just a frame, not sure that if you remember all the details, and then handle, a saddle, and that's pretty much it, right? But look at this one. This guy has forgotten to have that hop in the center and the chain also, and the pedal. This guy has forgotten to have those thingies, right? So it shows that we just have the idea of the major elements, and that is what actually happens by using filters to search for those major components and say this is a bicycle. That's how our brain works as well. And the last visualization, the code is not fine. The code doesn't work. I spent good amount of time before. This is this file, the last file, which works, the code that I provided, it works fine. Try it later. But the general idea of the last one is applying this code and applying filters to see in which part of the image, for instance, these are African elephants. You can recognize the patterns and say, okay, this is the part that, for instance, this is one of the filters, one of the high-level filters that we have. If we apply that, it is going to recognize the elephant calf here and the mother here, right? And that's pretty much it. It shows where they could find and the location of the object. The summary of the chapter says, ConvNets are the best tool for attacking visual classification problems. ConvNets work by learning a hierarchy of modular patterns and concepts to represent the visual world. The representations they learn are easy to inspect. ConvNets are the opposite of black box because you can have, for instance, you can demonstrate the filters. You can see what they do on each image, the way that we applied on the cats. You are now capable of training your own ConvNet from scratch to solve an image classification problem. And actually, I saw that some of our team members for the final project, they have used that. You understand how to use visual data augmentation to fight overfitting, and you know how to use a pre-trained ConvNet to do feature extraction and fine-tuning. And finally, you can generate visualizations of filters learned by your ConvNets, as well as heat maps of class activity. And by saying that, this is pretty much we need to know for the final. I'm gonna stop recording here. Just I again repeat it. Next week, sharp in the lecture time, we are going to have our final exam. I have already announced it. And the other thing is next week, this time, actually from 8 in the morning till 6 p.m., we will have online labs. So if anyone has any concern about their marks, they can show up and discuss. I will try to share a quick video and an Excel file to go through the marking schemes to make it more to make it clearer and more understandable. By saying that, thank you very much. I'm gonna stop recording.